Today we're going to focus on a method implemented and developed by a German mathematician named Leonhard Euler. And he's going to take what Newton was working on and just flesh it out a little bit. He's going to expand it and go a little farther. We're really just looking at the thought process, the thinking that some of these great mathematicians had to do before we had computers, before we had handheld calculators, and how they were thinking about derivatives and how they could use derivatives, and then how we can take their work and take our calculators and do even more, okay, using what they did as sort of our starting point and our launching point. So we're going to go with Euler's method, and he's going to approximate the values of different functions. So let's back up and take a look at Newton a minute. So this is how Newton got around the problem of not having a calculator and not being able to get accuracy to a lot of decimals. If he needed to evaluate points along a curve, he would start at a convenient point, all right? So pick a point that he did know on the curve that he was able to evaluate with pinpoint accuracy, okay? Something that was a nice whole number. And then he would use the method of moving away from that, using his idea of slope and derivative, and to calculate a rise over a run, or a run and then a rise. And he would do that to arrive at a new point. And he would figure, well, it's close enough. Okay, close enough to where I should be. If we're taking this equation and taking it all the way out, we can see that there is quite a big gap between where maybe he should be and where he ended up. But, that was as good as it got. Okay, that was as close as he could evaluate using his idea of a derivative. So what Euler did was he said, well, I'm not satisfied with good enough. How can we make this better? And so his method is to still start at that same convenient point and count off your run and then your rise. Okay, we're zooming in on that. And then from that new point, calculating again, recalculating a new run and a new rise. Okay, well, I guess the run is always going to be the same. That'll be a consistent value, but it would be a new rise. And that would keep the gap less. Okay, it would minimize the gap or the difference between his estimated point and the actual curve. It's just making micro adjustments every single time and then recalculate it again with a same run, but a new rise. And we're calculating this using the derivative because the derivative just is a value of slope, and coming up with another estimate. So it keeps the estimates a lot closer to the curve because it's adjusting the slope and it's kind of following the concavity of that curve as it goes, as opposed to Newton. If you stayed on Newton's tangent line the whole way, so staying out this whole way, where Newton would end up would be a lot bigger of a gap of a a difference from where it would be on the actual logarithmic curve there. So Euler's idea was, let's do some micro adjustments, okay, some incremental adjustments. All right, so step one, start at a convenient point. Step two, determine the slope so that you can count out your run and then your rise. Doing this by incremental values, okay? And then we talked about that, incremental values. Using those values to get to your new point. So we'll call that x1, y1. That was right here. Down farther, that one right there. And then repeating it again, calculating a new incremental run and rise, run and rise, run and rise over and over and over. So just keep repeating it until you end up at your desired value. And it will be a much, much closer estimate because the reason is that you're making micro adjustments in the slope that will allow you, instead of just following one tangent line and just going straight off your tangent line and staying on the same slope the whole time, you're making micro adjustments to the slope that will allow you to follow the curve a little bit more efficiently. Here's a curve that has a negative concavity and making the micro adjustments every single time. So you can see if you'd followed Newton and you'd taken the original and then just headed off the original is not taking into account that there is a change in direction of the function here, and so it's following the negative concavity. So Euler would say, no, let's micro adjust and let's find a new slope, and then micro adjust again, and then your micro adjustment on this last one ends up to be negative, which helps you follow the curve even more. If you want to, I've been doing all of this going to the right to left. If you want to go left to right, if you want to go the other direction, so suppose your point was over here and you want to follow that way, you're just going to use negative incremental values. So you'll have a negative incremental value of your slope and then adjust it to a negative incremental, and you're working your way backwards this way. That will help you follow the slope using Euler's method. So let me show you how it works. Okay, the incremental values we're going to use are going to be 0.1. So each time that'll be our run. We're going to run 0.1 to the right so that we can evaluate. Okay, we are starting with the initial condition that y is 2 when x is 1. So that gives me my initial starting value here. We're also given what the slope is, and the slope is determined this way. So that is my slope, and I'll be finding that in this column right here. So for the initial point, if I use the formula for slope to determine what the slope is going to be the x value of 1 plus 1 equals 2. All right, so the slope value is 2. That slope value of being 2, think of it as a rise of 2 with a run of 1, right? Up 2 over 1. Well, what if we ration that, if we prorate that, if we say, okay, I'm not going to rise 2, run 1. What if I only wanted to run 0.1, which is my increment right now? Okay, I've given that. What would the corresponding rise be? Well, if we want to keep the ratio the same, the rise would be 0.2. Those are the, it just keeps the ratio exactly the same, the proportions the same. And so my run would be, so this is the run, and I would have an 0.2 of a rise. So where do you end up? If you start at 1, 2, and you've now run 0.1, you end up at 1.1. And if you start at the y value of 2 and you've now risen 0.2, you end up at 2.2. So that's where I end up. So that's my temporary next point. Now I want to make an adjustment. So I'm going to take that next point. So this is now x1, y1. Remember, your initial is x0, y0. And now I'm going to take my next point. Okay, well, I want to figure out what the slope would be here. So according to the slope formula, it's the x value plus 1. So the slope value is 2.1. Again, that's assuming that I'm rising and running a full 1 value. So if I'm only going to run 0.1, then my rise would be 0.21. So now my new value, I've run another 0.1 increment, and now my rise gets me, if I add 2.1 or 0.21 to where I'm at 2.41, and that's the next point. And now I want to make a micro adjustment again. So now I'm at x2, y2. I'm at 1.2 and 2.41. Now what will the slope be? Well, it'll be 1.2 plus 1, 2.2. So my run is 0.1 to the right. My rise is 0.22. So I'll end up at 1.3 and then 2.63 if I add. That point becomes my x3, y3. And my slope will become 2.3 The run stays the same. All of these are always the runs. Oops, I noticed I just wrote something. I wrote run instead of rise. My rise would be 0.23, giving me a 1.4 and a 2.86. And that gives me my final incremental point. My slope here is 1.4 plus 1, so 2.4. I'm going to run. I will rise 0.24. So I'll end up at 1.5 comma. And then I'm going to add 0.24 to this, which gives me 3.10. And this is the final position, so that my Euler estimates that that's where I'll end up. And all these micro adjustments have moved me from my initial point, which was here, down to my final estimated point, which is here. So we're following an unknown curve, an unseen curve. It's a curve we don't even have an equation for. But by using the slope and making micro adjustments every single time, we can predict where the value at 1.5 would be with very high accuracy. All right, that was your first try at it. Let's just try another one. Okay, we're starting at the initial condition 2, 3. And so I apologize on your notes. You'll need to fix this to be 2, 3. I'm trying to estimate the function value at 1.5. So I want to end up down here at 1.5 and figure out. All right, so if I start at 2, 3 and I'm going backwards and I want to end up at 1.5. So I need to do that incrementally. So I'll be backing up to 1.9 comma something, 1.8 comma something, 1.7 comma something, 1.6 comma, and I'll end up finally at 1.5. So that's my goal. My slope that I'll be using incrementally will be connected to the derivative that I have right there. So I should be able to figure out my slope. All right, so at the initial condition, my slope is going to be 2x minus y. So that's 2 times 2 minus 3. So that's a slope value of 1. So I've got a slope value of 1, but I'm going backwards. Okay, I am working my way backwards. And so if the slope value was 1, then my rise over run would be 1 over 1. But I want to prorate that, or to do it by multiplication. So that should be, if it's negative 0.1, then what should the numerator? Well, it should be the same, negative 0.1 as well. So my y is also negative 0.1. So what are the new values? So now I'm at 1.9, so I've run backwards. And instead of rising, I'm falling down, going down. So I'm at 1.9, 2.9. So I've gone down, backwards and down. Okay, what will the slope be this time? Well, I'm probably going to want my calculator to help me out with this, because I am going to have a little bit more complicated multiplication and subtraction to do. So it will be 2 times x, which is now 1.9, minus y, which is now 2.9. So what will the new slope be? So if I multiply that, so that'll end up being 3.8 minus 2.9. So I'll be looking at 0.9. So then what would the increment be? It's really just the multiplication of the slope and the increment. So I could take the slope and the increment and just multiply those. It's just the product is how you keep the prorated ratios the same. And so we will be falling, basically not rising, 0.9. All right, so now I'm at 1.8, and then I'm subtracting, and I'll be at 2.81. Okay, that's by subtracting the the x increment from the x value and the y increment from the y value. All right, we keep going again. So now this is 2.81, so this is my new x and y. My slope will be 2x minus y, so 2 times 1.8 minus 2.81. And then what will that give me? I think I better give myself a little more space here. 2 times 1.8 minus 2.81. So it's 0.79. So if I multiply, then my run is going to be 0.079. So my x is going to go down by 0.1, and my y is going to go down by 0.79. Excuse me, 0.079, and I'll get 2.731. Okay, so now I'll adjust from that, a micro adjustment. So my slope will be 2 times x minus the y value, 0.669. So that would be negative 0.0669 to micro adjust that. So that'll decrease me down to 1.6 and 2.6641. All right, so we're almost there to the point where we're going to make our final incremental adjustment. All right, so 2 times 1.6 minus 2.6641. That's 0.5359. So a resulting fall of 0.05359. So I'll end up with, let me erase this so I can. $2.61051. So our original point of 2, 3, as we micro adjusted backwards, ended up with a resulting point of 1.5 and 2.61051. All right. So you're probably thinking, oh heavens, am I going to have to do all of this multiplication, subtraction, all these decimals? But thankfully, there's a program which you should have loaded on your calculator. We got everything you needed for the year. So we can take that Euler's program, don't say Euler, that's not how it's pronounced, Euler's program, and you should be able to run this so that you can come up with these estimations a little bit more quickly. So that's the advantage. Euler had to do it all by hand. We can now use the power of the graphing calculator. So we just have to know how to use it. So in your y1, you're going to put the value of the slope. So x plus y. And remember, you can use y by just using your alpha and then your 1 key, your numeric 1 key. That'll get you the y. So put that into y1. That is what the slope is. You're just going to run that in. Okay. Then when you execute your Euler program, it's going to ask you what the initial condition is. So it'll ask you what x is. All right, you say x is 2. And you put in that your y is 0. Then it's going to ask you what your increment is. So you're going to have to figure that out. So if you are starting with an initial condition of 2, and you need to get to a condition of 3 incrementally 5 times, so then that would be the 5 increments are going to have to be that space of 1 unit divided into 1/5 of that, so 0.2. So your increment value will be 1/5 or 0.2. And then you're going to run your program, and you're going to notice it's going to give you all of the incremental values. The first time you press enter, you'll get 2.2, 0.4. That's the first incremental adjustment. You hit enter again, you're going to get 2.4 and 0.92. That'll be your second incremental adjustment. Then you'll get 2.6 and 1.584. 2.8 will be your fourth incremental adjustment, and that'll be 2.4208. And your final incremental adjustment is going to get you to the desired value of 3, which will be 3.46496. So that will be the result. So 3.46496 is the approximation. And you should be able then to answer the over or under question for the actual value. In other words, you should be able to approximate based on the concavity of the function that you're looking at. So let's think about what the second derivative would be. So the second derivative will be the derivative of what we're working with. So let's look at x plus y. The derivative of x is 1. The derivative of y is dy dx. So this would be 1 plus what dy dx was. So that's my second derivative. And all of the values I'm dealing with, all of these incremental values, are all positive. And since these are all positive, then my second derivative would always be greater than 0, no matter what, because I'll be working with positive numbers. I'll add them together, I'll add 1, and I'll get positive numbers. So since d2, the second derivative, is greater than 0, then f of x is concave up. And if this is concave up, then Euler will underestimate. Okay, so let's picture that. Let's look back at one of those other slides where we saw a concave up picture. So that would be like this one. This is a concave up section, and Newton would underestimate, and so would Euler. Euler's always going to underestimate. It's going to be more accurate, but it's still going to be an underestimate of where you were. As opposed to concave down, then a tangent line and Euler will always overestimate. So we can use concavity much in the same way that we have been with tangent lines, and we can conclude that the value we got, although more accurate, is going to ultimately be an underestimate of where we need to be. Okay, if you don't have that Euler's program on your calculator, please come see me as soon as you can so I can load that to your calculator. All right, thanks.